Hello everyone, I'm Zitao Li. I'm here to introduce our VLDB paper, Differential Private Vertical Federated Clustering. This is a joint work with Professor Qianhao Wang and Professor Ninghui Li. Differential privacy is a popular notion for protecting individual users' information. A mechanism satisfies differential privacy if and only if given any dataset as input, the mechanism's output should be somehow follow similar distribution as taking its neighboring dataset as input. By neighboring dataset, we mean a pair of dataset with only one user's data difference. So in this example, we can see that if we apply Laplace mechanism to the count of user with age larger than 20, then no adversary can have a high confidence on whether user 4 is actually in the dataset by looking at just the output, even if the adversary knows all other three users' ages. In this paper, we focus on the classic problem, k-means clustering. Given a dataset with multi-dimensional data, the k-means clustering problem is to find a set of k centers so that the sum of the distance of the data point to the closest center can be minimized. The centers satisfy this property can usually be used as synopsis of this dataset. But computing this is the centers satisfy exactly the condition is the NP-hard problem. The well-known Lloyd algorithm can only produce a heuristic solution for the problem. In general, people use beta lambda approximate to describe how good a polynomial time running algorithm can solve the problem. It means that the cost of the center output by this algorithm is at most beta times the optimal cost plus lambda. If we don't consider privacy, many algorithms can ensure lambda to be zero, and only the multiplicative factor is non-zero. However, if we consider enforcing differential private k-means algorithm, then the lambda has been shown that is unavoidably larger than zero. In this paper, we consider solving k-means problem in a challenging vertical federated learning setting while providing privacy protection for the local data. In the central setting, one can easily compute the distance between the data point to any temporary center, and then update the center accordingly. However, in the vertical setting, a user's data are distributed on multiple data holders. Calculating the distance of the user data to the center involves communication between the data party and the server. This operation can be very expensive and also very easy to leak too detailed information about a user's data point. There is a previous paper proposed a solution to solve the k-means clustering problem in the vertical setting, but does not consider privacy protection. The key idea of this solution is to let each data holder to first perform k-means clustering on their local data set first. And then with the generated local center, they can obtain the corresponding membership, which is the users are included in the cluster to the corresponding center. Then the data party can share this information to the central server. The central server can build a grid, where the grid node is the Cartesian product of the local centers, and the weight of each grid node is the cardinality of the intersection of the corresponding membership. Finally, the server can take this grid node as input and run another k-means algorithm to generate the final centers. The author showed that the generated center has cost at most beta times the optimal, where the beta depends on beta 0, which is the performance of the local k-means algorithm. If beta 0 is close to 1, then the final beta here will be close to 9. As mentioned, this algorithm does not consider privacy protection. So both the shared local center and the membership information can leak privacy. For the local centers, we can apply any differential private k-means algorithm to enforce privacy protection, but how to share the membership information is still unclear, so which is also the main focus of this project. Based on the previous solution, maybe as a simple improvement toward privacy protection is to only share the cardinality of the local membership and use Laplace mechanism to provide privacy guarantee. For the server side, to calculate the weight, we need a strong assumption that assuming the attribute of one party are independent of the other one on the other party. So we can, with this strong assumption, we can calculate the weight by just multiplying the total user number with the portions of the user fall in the corresponding clusters. Clearly, this approach can provide privacy protection, and it is very communication efficient because it only share the private centers and the private cardinalities, but it totally ignores the correlation in the inter-party attribute, and thus there is no utility guarantee with this method. Another approach to share the membership while protecting privacy is to apply local differential privacy protocol on the center that each user is assigned to. So after the server receives this randomized local membership information, it can append all the local report for the same user together, and then calculate an unbiased estimate for the intersection cardinality as the weight for each grid node. This approach, as we showed, can provide privacy protection because it depends on the LDP protocol, and also maintains some correlation of the inter-party attribute. But the LDP protocol will usually introduce large noise. In this paper, we propose to share and estimate the membership information via Fladrien-Martin sketch. FM sketch was originally designed for cardinality estimation. For example, how many users are in a large set. Assuming each user has a unique user ID, the high-level idea of FM sketch is to use a geometric value hash function to hash the user ID. The output of the hash function can be considered as random samples from a geometric distribution if the hash key is uniformly sampled. The FM sketch only contains the maximum of the hash values, and the cardinality can be calculated by this FM sketch. To reduce the estimation variance, people usually use multiple hash functions to repeat the hashing, and use the harmonic mean of the output as the final estimate. There are many advantages of FM sketch. One is that it has been proved that it can satisfy the differential privacy if we add some phantom element and lower bound. Also, it can support the union operation. That is, if we want to calculate the FM sketch for the union of two sets, we just need to take the maximum of the two FM sketch for the corresponding sets. With all these good property, we apply FM sketch into our problem. We let each data party to generate FM sketch for each of the membership cluster. And this process will repeat m times with m different hash functions. And then the FM sketch will be shared to the server. The server will calculate the cardinality with the FM sketch and using the inclusion-exclusion law to calculate the final intersection cardinality. The computation process detail can be found in our paper. We also derived the cost upper bound for our method. According to our result, the multiplicative factor will be like the following. So if both beta prime and beta 0 are close to 1 according to the latest result, then our final beta will be close to 10, which is slightly larger than the non-private algorithm. In addition, the additive error will grow with both the number of centers and the number of parties involved. Another advantage of our proposed method is the communication cost. The communication cost is independent of the number of data points in the dataset. It only related to the number of FM sketch used in the process. So when the number of users is large, then our algorithm can gain advantage in that. There's still challenge that when the number of data party increase, the number of nodes will increase in the grid will increase exponentially. So the number of users for in each intersection will shrink exponentially. To improve the empirical performance when there are more than 2 data parties, we provide a heuristic optimized algorithm. This operation it would be the same on the client side. You just need to generate the FM sketches. But on the server side, we will only decode the pairwise intersection for the pairwise to calculate the pairwise intersection cardinality directly. And then we will take this pairwise cardinality as constraints and solve a convex optimization problem for the final intersection cardinality we want. We provide some empirical results of our algorithm in the paper. As is shown in the figure, when there are 2 data parties, our proposed mechanisms, both the basic estimate and two-party and the heuristic two-party estimate can outperform other vertical algorithm. And when the number of data party increase to 4, we can see that our heuristic two-party estimation with FM Sketch can gain a significant advantage over all the other vertical federated learning approaches. So more experimental results can be found in our paper as well. Yeah. To make a conclusion, the major contribution in this paper is a differentially private vertical federated learning k-means clustering algorithm with an untrusted central server based on FM Sketch. And we also propose an improved heuristic algorithm for the case with only with more than 2 data parties involved. Yeah, that's all of the contribution. Thank you for your listening.